Welcome to the Sleepy Scholar. It's lovely to have you here tonight. Wherever you are right now, however the day has treated you, you've arrived somewhere quiet. Maybe you're under a blanket that's finally warmed up around you. Maybe there's a lamp still on in the corner, throwing soft gold across the wall, and you keep meaning to reach over and turn it off. Maybe you're on a train or a couch, or lying flat on your back, staring up at a ceiling you can't quite see in the dark. Wherever you are, I'm glad you found your way here. Settle in. There's no hurry tonight. There's nowhere to be. And before we begin, just a small thing. If you enjoy these slow journeys, if you'd like more nights like this one, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you already here, already subscribed, already part of this, thank you. Truly, you make this possible. So tell me, before you drift off, where in the world are you listening from tonight? What time is it in your corner of the dark? I always love to imagine all of you scattered across the planet, all of us awake in the small hours, all of us looking up at the same sky in our own way. Now, here's my one promise to you, the same one I always make. We're going to move slowly tonight, gently. There's no test at the end. There's no part you have to remember. If you drift off before we're done, and I genuinely hope you do, that's perfectly fine. The ideas will still be here. The universe isn't going anywhere. You can come back to it tomorrow or the night after and pick up wherever your mind let go. I'll try my best not to make this so interesting that it keeps you awake. Although I'll be honest with you, tonight's story is a strange one, so if it does keep you up a little, well, at least you'll have learned something lovely. A fair trade, I think. So let me tell you what we're going to drift through tonight. There's a planet, we think. We're not entirely sure, and that uncertainty is part of what makes it so haunting, but let me say the thing first, and then we'll take it apart slowly, piece by piece, like unwrapping something delicate. There's a planet, a world, maybe a little smaller than Saturn, somewhere out in the cold. And here's the part that does something funny to the chest if you let it really land. That planet, if it's real, is not in our galaxy. Not in the Milky Way, not anywhere near us. It's out in another galaxy entirely, a separate island of stars hanging in the dark, 28 million light years away. 28 million light years. Sit with that number for a moment because it's the kind of number that sounds almost made up. A light year is the distance light travels in a single year, and light is the fastest thing there is, fast enough to circle the Earth more than 7 times in 1 second. In a single year, that beam of light crosses about 6 trillion miles. Now take that almost unimaginable distance, that single light year, and multiply it by 28 million. That's how far away this little world might be sitting tonight, quietly orbiting while you lie here under your blanket. The light we're catching from that galaxy right now, the faint signal that hinted this planet might exist, it left its source 28 million years ago. It set out across the dark long before there were any people to wonder about it. It's been traveling and traveling and traveling through emptiness so vast and so silent that the word empty hardly does it justice. And only now, just recently, did it arrive here, fall into our telescopes, and whisper that maybe, there's a planet out there. That's where we're going tonight. We're going to drift slowly out past everything familiar, out past our own galaxy entirely, to the edge of what we can even detect. And we're going to ask the question that should be impossible to answer. How on earth, or rather, how from Earth, could anyone possibly see a single planet from 28 million light years away. But I'm getting ahead of myself. Let me slow down. Let me give this room to breathe, because this is the part worth lingering on. The planet has a name. A clumsy, technical, very much not poetic name, the kind astronomers tend to give things when they're being careful rather than romantic. It's called M51 ULS-1b. Don't worry about remembering that, you won't need it. But I'll tell you what each piece means, slowly, because each piece is a little door into the story. The M51 at the front, that's the galaxy, the home. M51 is a catalogue number, and the galaxy it points to has a much lovelier name. It's called the Whirlpool galaxy. And once you've seen it, you never forget it, because it really does look like a whirlpool. A vast glowing spiral, two great arms of starlight winding around a bright golden core, like cream stirred slowly into coffee and frozen halfway through the swirl. If you've ever seen a picture of the most beautiful galaxy, the textbook spiral, the perfect pinwheel hanging in space, there's a very good chance you were looking at the Whirlpool. It's one of the most photographed objects in the entire night sky. We'll come back to it later, because the Whirlpool has a secret of its own, and it's not the gentle, serene thing it looks like. But for now, just hold the image. A perfect glowing spiral, 28 million light years away. That's the home of our maybe planet, the ULS-1 in the middle, that points to a very particular object inside that galaxy, a specific bright source we'll get to know in a little while. And the little B on the end, that's the planet itself. Astronomers have a habit of naming the star or the central object with a capital letter, and then naming the planets that orbit it with small letters starting at B. So the B is the world. The shy little B at the very end of that long technical name is the thing that, if it's real, just rewrote one of the oldest assumptions we had about the cosmos. And what was that assumption? Well, let me paint you the picture of how things looked right up until very recently. The settled, comfortable, tidy version of the story. Because to understand why this discovery matters, you have to feel how the world looked the day before it. For most of human history, of course, we didn't know there were any planets beyond our own little family. We knew the Sun and the handful of worlds that go around it, Mercury, Venus, our own Earth, Mars, the great gas giants Jupiter and Saturn, and the cold, distant ones beyond. That was the solar system. That was, for the longest time, the whole catalogue of known worlds. 8 or 9 planets, depending on how you feel about Pluto, all circling one ordinary star. And people wondered, of course, surely there must be other planets out there, around other stars. It seemed almost obvious, but wondering is not the same as knowing, and for a very long time we simply could not see them. A planet is small and dark, and it doesn't shine with its own light. It only reflects the light of its star faintly, like a moth fluttering next to a lighthouse. And from across the unimaginable distances between stars, that faint reflected glimmer is utterly swamped, drowned, lost in the blaze of the star sitting right beside it. Trying to spot a planet next to its star from light years away is like trying to see a single firefly hovering just beside a stadium floodlight from miles and miles down the road. The floodlight wins every time. So for decades, even as we were certain other worlds had to exist, we couldn't actually find a single one. Other planets were a matter of faith, not of fact. And then slowly, cleverly, that changed. Astronomers learned new tricks, ways of catching a planet not by seeing it directly, but by noticing its effects. They learned to watch for the tiny, telltale wobble a planet's gravity gives to its star, a faint tug back and forth as the unseen world pulls on it. And they learned to watch for something even simpler, even more elegant. They learned to watch for shadows. If a planet's orbit happens to be lined up just right so that from our point of view, the planet passes directly in front of its star, then for a few hours that planet blocks a tiny sliver of the star's light. The star dims just slightly, just for a while, and then brightens again as the planet moves on. We call that a transit, a little eclipse. And if you watch a star patiently for long enough and you see its light dip in that careful, regular repeating rhythm, dim, then bright, then dim again, like a slow heartbeat, you found a planet. You found it by its shadow. And once we learned those tricks, the floodgates opened. The discoveries came pouring in. One planet, then 10, then hundreds, then thousands. Worlds of every kind. Scorched, rocky worlds hugging their stars so close that a year lasts only days. Vast, puffy gas giants bigger than Jupiter. Frozen wanderers in the dark. Worlds with two suns in their sky, like something out of a dream. By the time of the discovery we're talking about tonight, astronomers had confirmed well over 4,000 planets beyond our own solar system. Today that number has climbed past 5,000 and it keeps rising. 5,000 other worlds, a whole bustling census of planets where once there were none we could see. But here's the thing, here's the quiet, tidy assumption sitting underneath all of those 5,000 worlds. Every single one of them, every last one, was found inside our own galaxy. Inside the Milky Way. All 5,000 of them. Our entire collection of known planets, every world we'd ever confirmed in the whole history of the search, was tucked into one galaxy. Our galaxy. And not even spread evenly across it. Most of them were found relatively nearby, in our own little neighborhood of the Milky Way, within a few thousand light-years of home, which sounds enormous. A few thousand light-years is a distance that would take light thousands of years to cross. But on the scale of the universe, it's the front porch. It's barely off the doorstep. We'd been finding planets, yes, thousands of them, but only in our own backyard, only down our own street. And that became the quiet shape of things, the settled world view. Planets were a Milky Way phenomenon. Not because anyone had decided they could only exist here, of course not, but simply because here was the only place we could possibly detect them. The tricks we'd learned, the wobbles and the shadows, all depended on watching individual stars one at a time, close enough to study in detail. And once you go beyond our galaxy, the stars blur together. Another galaxy, even a nearby one, is so far away that its hundreds of billions of stars smear into a single soft glow. You can't pick out one star from that distance, let alone watch for the faint flicker of a planet crossing in front of it. It was simply, flatly, beyond reach. So that was the line. The frontier. Planet hunting stopped quietly at the edge of the Milky Way. Beyond that edge, in all those billions of other galaxies scattered across the universe, there must surely be countless trillions of worlds. But we would never see them. They were forever out of reach. A reasonable person, an expert even, would have told you not long ago that finding a planet in another galaxy was, for all practical purposes, impossible. Not unlikely, impossible. The signal would be too small, the distance too vast, the stars too crowded. It couldn't be done. And that, my friend, is exactly the kind of tidy, sensible, settled assumption that the universe loves to quietly take apart. Because in September of 2021, a team of astronomers published something that broke right through that frontier. Not a planet in our backyard, not a planet a few thousand light-years away. A possible planet, a candidate, sitting 28 million light-years from here in the Whirlpool galaxy. far, far outside the Milky Way. The first hint of a planet ever found in another galaxy. Let me give you a feeling for just how big a leap that is. I said most of our planets were found within a few thousand light years. This one, if it's real, sits 28 million light years away. That's not a little farther. That's not twice as far, or 10 times as far. It's roughly 10,000 times farther than the familiar hunting ground where almost all our planets had been found. Imagine you'd spent your whole life exploring your own neighborhood, every street within a mile of your front door, and you thought that was the whole of the explorable world. And then someone showed you a photograph from 10,000 miles away from clear across the planet and said, "We think there might be a house here too." That's the size of the jump. In one single discovery, the frontier of where we'd ever found a planet leapt outward by a factor of 10,000. It's the kind of result that makes you go quiet for a second. Because it doesn't just add one more planet to the list of 5,000. It changes the shape of the list entirely. For the first time, the list might reach beyond our own galaxy. For the first time, we'd have evidence, fragile, contested, but real evidence, that the worlds out there aren't only in our galaxy. They're everywhere. In other galaxies, in other spirals winding through the dark, millions of light years away, the thing we always assumed but could never show. Now, I have to be honest with you, because honesty is part of what makes this story so lovely, and because I'd never want to oversell a thing to you in the dark. This planet is not confirmed. It's a candidate. A very, very good candidate, with very careful evidence behind it, but a candidate all the same. And the reasons it can't quite be confirmed are some of the strangest and most beautiful parts of the whole story, and we'll get to them slowly a little later tonight. There's a haunting catch buried in this discovery, something about time, about waiting, about how long we'd have to hold our breath to be sure, and I'll save it because it deserves its own quiet moment. For now, just hold both halves of the truth gently in your hands at once. We might have found the first planet in another galaxy, and we might never be able to prove it. Both things true at the same time. But let me come back to the question that should be keeping you awake, in the good way. The question I promised we'd circle. How could anyone possibly detect a planet from 28 million light years away when I just spent all this time telling you it was supposed to be impossible, when the stars at that distance blur into a smear and a planet's reflected light is a moth beside a lighthouse, and the whole frontier was supposed to stop at the edge of our own galaxy? Because something had to be different. The old tricks, the wobble, the ordinary shadow, they simply don't work at that range. So the astronomers must have done something else, something clever, something that turns the impossible into the merely very, very difficult. And they did. The trick they used is so elegant and so strange that when you finally understand it, it has a way of feeling almost inevitable, the way the best ideas do. The kind of idea where you think, well, of course, once someone says it out loud. But to get there, I have to tell you about the thing this planet orbits, because it doesn't orbit a normal star, not a calm, steady, sun-like star like our own. Its sun, if you can even call it that, is something far stranger, something violent, something that was in a sense already dead. But I'm getting ahead of myself again. We have all night. Let me slow back down. Let me first just give you the shape of the event itself. The actual thing the astronomers saw, the moment in the data that started all of this. Because it's wonderfully simple to picture, even if everything underneath it is exotic. They were watching a bright source in the Whirlpool galaxy. A particular point of brightness glowing steadily, the way these things tend to do. And then, over the span of a few hours, that brightness dropped. Not a little. Not a faint dip of 1% the way an ordinary planet dims an ordinary star. It dropped all the way to essentially nothing. The source, which had been shining away, went dark completely. A total blackout lasting about 3 hours, and then just as gently, it came back. The brightness climbed back up to where it had been, and the source carried on glowing as if nothing had happened. 3 hours. A clean, smooth dip, down to 0 and back. Something had passed in front of that bright source, something that blocked it utterly, completely, for 3 hours, and then moved on. And the most natural thing in the world to ask, the thing you might be asking right now in the dark, is, well, lots of things could block a light. A cloud could drift in front of it. The source itself could just flicker the way a candle gutters. Why a planet? Why leap all the way to the first planet in another galaxy from a single 3-hour dip in brightness? Good, hold on to that question because it's exactly the right one, and the answer is one of the loveliest pieces of careful detective work in modern astronomy. The way they ruled out the clouds, the way they ruled out the flickers, the way they narrowed it down, step by patient step, to a solid object the size of Saturn. That's a story all its own, and we'll walk through it slowly. There's a particular clue, something about the color of the darkness, the flavor of the shadow, that pointed away from a cloud and towards something solid. I'll explain it gently when we get there. No rush. But first, the deeper mystery. Because even if something solid passed in front of that source, even if it was indeed a planet, we still have to answer the impossible part. A planet is small. A galaxy is 28 million light-years away. How could a small, dark planet blocking a light from that unthinkable distance possibly produce a dip big enough for us to notice at all? When I told you that across those distances an ordinary planet's shadow is hopelessly drowned out, I wasn't exaggerating. So what's different here? Why does the shadow work this time when it shouldn't? The answer is hiding in the kind of light they were watching. Because they weren't watching ordinary light. Not the visible light your eyes can see, not the gentle glow of a normal star. They were watching X-rays, and that single difference, watching in X-rays instead of invisible light, is the whole secret. It's the hinge the entire discovery turns on. It's the reason the impossible became possible. But to understand why X-rays change everything, I have to tell you what kind of object pours out X-rays like that in the first place. And that brings us right back to the planet's strange, violent, not quite a star, sun. So let me set the scene for where we're going next, and then we'll let it rest for a moment. Imagine, out there in the Whirlpool, a place where a star has already died, not faded gently, exploded. And in its place, something small and dense and almost unbelievably extreme is left behind, the crushed corpse of that dead star, and it's feeding, pulling matter off a companion beside it. And as that matter spirals in, it heats to such ferocious temperatures that it screams out X-rays across 28 million light-years of empty space. That scream of X-rays is the bright source. That's the thing that went dark for 3 hours. And the size of that screaming hot region that turns out to be the key to everything. But I'm getting ahead of myself once more, and you're meant to be drifting, not racing. So let that image settle in for now. A dead star, feeding, glowing in X-rays. A bright point in a beautiful spiral galaxy, 28 million light-years away. And something small and dark and possibly a whole world unto itself, passing silently in front of it for 3 hours, casting a shadow we somehow managed to catch. We'll take it apart slowly. We'll understand exactly why that tiny dead star is what made a faraway planet visible when a normal star never could. We'll meet the people who found it and the great observatories floating high above the Earth that gathered the light. We'll understand the careful reasons it's still only a candidate and the haunting catch that means we might be waiting a very, very long time to ever know for sure. And we'll wander eventually to the Whirlpool itself, that perfect, glowing, photogenic spiral, and discover that its beauty is not the calm, serene thing it appears to be, that it's hiding a slow act of violence right out in plain sight, and that this violence, strangely, beautifully, is woven into the very same story as the planet. For now, though, there's no need to hold any of it tightly. Let the number do its quiet work. 28 million light-years, a possible world hanging in another galaxy, found not by any light it gives off, but by a shadow it cast, a 3-hour darkness across the death glow of a star that had already died. Every other planet we'd ever found, all 5,000 of them, sat inside our own galaxy, close to home, down our own street. And then, in one quiet result published in 2021, the frontier jumped 10,000 times farther out, clear into another spiral, and the universe gently took apart one more thing we were sure we understood. Breathe. There's so much more to come, and all of it can wait until you're ready. Just rest here a moment, on the edge of this strange and lovely thing, and let it be enough for now that somewhere out there, 28 million years away by the speed of light, a small, dark world may have crossed in front of a dying star and cast a shadow long enough and patient enough to finally reach us here in the dark. Welcome to the Sleepy Scholar. It's lovely to have you here wherever you are, whatever hour it happens to be in your corner of the world. Maybe there's a lamp still on somewhere near you. Maybe the blanket is pulled up just right, and the room has gone quiet the way rooms do at this time of night. Settle in. You don't have to do anything now but listen, and even that you can do loosely, the way you'd half listen to rain. And before we drift any deeper, just a small and gentle thing. If you enjoy these slow journeys into the dark, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you already here, already part of this, already coming back night after night, thank you. Truly. I'd love to know where you're listening from tonight and what time it is in your little pocket of the world. Leave it in the comments whenever you like. There's no rush. There never is here. Now, let me say the thing I always like to say at the start because I mean it. If you fall asleep before we reach the end, that is perfectly, completely fine. That's allowed. That's almost the point. The ideas will still be here when you wake, patient as stones. You don't need to follow every turn. You don't need to remember any of it in the morning. We're going to move slowly tonight, softly, one strange and beautiful piece at a time. And if your eyes close somewhere in the middle of a sentence, then we'll just have done our job. I'll try not to make this so interesting it keeps you awake. But if it does, well, at least you'll have learned something lovely on your way to sleep. A fair trade, I think. So let's begin where the strangeness begins. There is a darkness I want to tell you about, a very particular darkness. It lasted about 3 hours and then it ended, and in those 3 hours, something was completely, utterly switched off. Not dimmed, not softened, switched off the way you'd switch off a light in a room before bed. One moment there was a bright source pouring out a fierce, steady glow, and the next, across that source, the brightness fell all the way down to nothing at all, sat there at nothing for 3 slow hours, and then, just as gently, climbed back up to where it had been. A blackout. A clean, total 3-hour blackout, far, far away in the dark. That blackout is the whole reason we're here tonight, because of how something can vanish and what it might mean when it does. Now hold that image for a moment, the light that went dark, and let me set it where it belongs. Because this didn't happen close to home. It didn't happen in our own neighborhood of stars. It happened across a gulf so wide, it's almost rude to say the number out loud in a calm voice. 28 million light years. We've said it already, I know, but let it land again, slowly, because numbers like this need to be approached the way you'd approach something sleeping. 28 million light years. The light that carried this little story to us left its source 28 million years ago, when there were no humans yet, no cities, no telescopes, nobody to wonder. And it has been traveling quietly the entire time, just to bring us the news of a 3-hour darkness. And here's the part that I find genuinely lovely, the part that makes me want to whisper it. Every other planet we have ever found, every single one, all 5,000 and more of them, lives inside our own galaxy, inside the Milky Way, down our own cosmic street, more or less. We'd gotten very good at finding them, these worlds, circling other suns, but always they were close, always within a few thousand light years, always home in the grand sense of the word. The whole vast catalogue of known planets sat tucked inside one galaxy, like a family who'd never once left their own town. That was the settled picture, you see. That was the quiet assumption underneath everything. Planets were a nearby thing, a Milky Way thing, a here thing. Of course they existed elsewhere, scientists thought, surely they must, but finding one in another galaxy? That belonged to the realm of someday, of maybe of not in our lifetimes. The distances were simply too cruel. A planet is small and dark and quiet, and the space between galaxies is a vastness that swallows small, dark, quiet things whole. You couldn't see a planet that far. You just couldn't. Everyone knew that. And then came the blackout. If this one candidate world is real, and we'll talk carefully about that little word, candidate, because it matters more than you might think, then it does something almost cheeky to that settled picture. It doesn't nudge the frontier of where we've found planets. It doesn't extend it a little. It picks the whole frontier up and hurls it roughly 10,000 times farther out, 10,000 times, from down our own street, suddenly all the way out into another spiral, entirely into a different island of stars hanging in the dark. The map didn't grow at the edges. The map got a brand new continent nobody thought we'd reach. The galaxy where this all happened has a name, several names really, the way old and beautiful things tend to. Officially it's catalogued as NGC 5194. Astronomers also call it Messier 51, or just M51 for short. But you've almost certainly seen its other name, its lovely name, the one it earned by being one of the most photographed objects in the entire night sky, the Whirlpool galaxy. And if you've ever seen a picture of a galaxy in a textbook, the perfect kind, the kind with grand, sweeping, glowing arms curling out from a bright core like cream stirred slowly into coffee. There's a very good chance you were looking at this one. It's the postcard. It's the showpiece. It's the one we point to when we want to say, this is what a galaxy is supposed to look like. And it sits about 28 million light years away, turned almost perfectly face on toward us, as if it were posing, as if it wanted to be seen. We'll come back to the Whirlpool later, and when we do, I'll tell you a secret it keeps, because that serene, glowing perfection is not quite as peaceful as it pretends to be. There's a slow violence hiding in those gorgeous arms. But not yet. That's a story for further into the night. For now, just picture the prettiest galaxy you can imagine, hanging there, calm and bright, and impossibly far, and know that somewhere inside it, against one tiny, fierce point of light, a shadow passed for 3 hours. So that's the shape of the mystery we're settling into tonight. A possible planet, the very first one ever hinted at beyond the Milky Way, found in the loveliest galaxy in the sky, 28 million light-years away, discovered not by any glimmer it sends us, because it sends us nothing, but by the simple fact that for 3 hours it got in the way of something brighter, and that something went dark. And already, I imagine, a question is forming, even as you drift. A perfectly sensible, slightly stubborn question. How? How could anyone with any instrument sitting here on one small planet possibly notice a single world blocking a single light across 28 million light-years of empty dark? It sounds impossible. It sounds like trying to spot a moth crossing a candle flame in a city on the far side of the Earth. The planet is so small, the distance is so monstrous. The thing being blocked must be lost in the glare of an entire galaxy's worth of stars. It's a good question, it's the right question, and the answer is the most surprising and clever part of this whole strange tale, because the trick isn't that astronomers found a way to see something faint. The trick is far stranger than that. It has to do with just how small, how almost unbelievably tiny the thing that went dark really was. Smaller than a star, smaller than you'd ever guess. And we'll get to that slowly, gently, in just a little while. So, let's start with the ordinary way we find planets, the familiar way, the method that has given us those 5,000 and more confirmed worlds scattered through our galaxy like seeds on a dark blanket. When a planet crosses in front of its star, when it walks from our perspective right across the face of that glowing disk, it blocks a tiny fraction of the starlight. Just a fraction. A small shadow on a large lamp. If the planet is roughly Jupiter-sized, enormous by planetary standards, it might block about 1% of the star's light. 1%? If it's Earth-sized, considerably smaller, it might block 0.1%, even less, a whisper of a dimming, a barely perceptible flinch in the brightness. But here's the thing, that flinch is enough. For a nearby star, just a few hundred or a few thousand light-years away, our telescopes are sensitive enough to catch it. Instruments like NASA's Kepler Space Telescope and later TESS stared at fields of thousands of stars at once, patient as stones, watching for those tiny, regular dimmings. And slowly, painstakingly, the list of known exoplanets grew. Hundreds became thousands. Every one of them found by that same patient subtraction. Here is the brightness, and here, periodically, is a small shadow, less than 1%, and we say, a planet. Now put that same method to work on a star in the Whirlpool galaxy. 28 million light-years away. The star itself, even a bright, massive, luminous star, is a point of light so faint it's invisible to the naked eye, invisible even in modest telescopes, utterly drowned in the collective glow of M51's hundreds of billions of other stars. Even if we could isolate that single star's light, even if we could measure it precisely enough to watch for changes, a planet passing in front of it would dim it by a fraction of a percent. 1% perhaps if the planet were huge, less than that if smaller. Across 28 million light-years, that fractional change is not just difficult to detect, it is, for all practical purposes, completely undetectable. The numbers don't even come close to working. It would be like trying to measure whether a single candle somewhere in another city is 1% dimmer than it was an hour ago. The signal is real technically, but the noise, the vast distance, the overwhelming background light, the limits of any instrument buries it so completely that it might as well not exist. So for a long time, the question of planets in other galaxies wasn't really a question anyone expected to answer. Not yet. Perhaps not ever. The Milky Way is our planetary neighborhood. Other galaxies were, for this purpose, simply too far. The frontier of known exoplanets stopped at the Milky Way's edges as definitively as if there were a wall. And then someone thought of something different, something that changed the scale of what was possible. The thought at its core was this: what if the light being blocked isn't a star? What if the light being blocked is something much, much smaller? Because here is a fact about the universe that takes a moment to sit with. Not all bright things are large. Some of the most luminous sources in the X-ray sky, sources burning with extraordinary, almost absurd intensity in their tiny, fierce ways, are physically smaller than a city. Smaller, in some cases, than a large mountain. They are the remnants of dead stars, the dense and violent afterlives of suns that ended in catastrophe, and they shine not in visible light that our eyes or ordinary telescopes would catch, but in X-rays. Hard, penetrating X-rays, the kind that in a doctor's office pass through muscle and photograph bone. These objects are called X-ray binaries. The name describes their architecture, a binary meaning two objects in orbit around each other. One of them is a normal star, usually a large, hot, luminous one, a blue-white giant burning its fuel at a ferocious rate and therefore not long for the universe. The other is the remnant of a star that already died, either a neutron star or a black hole. Both of these are extraordinary objects in their own right, and we'll come back to what makes them so. But for now, the important thing is the interaction between them. The normal star, being large and hot, loses material from its outer layers. A stellar wind, a slow shedding of gas that drifts out into space. And when that gas drifts close enough to the compact companion, the neutron star or the black hole, gravity catches it, pulls it in. The gas spirals down faster and faster, compressing, heating, until it becomes searingly, blindingly hot. This infalling material forms a disk around the compact object, a swirling, flattened ring of superheated plasma, and the innermost part of that disk, the region closest to the neutron star or black hole, radiates at extreme temperatures, not in visible light, in X-rays. That inner region, the heart of all that violence, where the X-rays are born, is very, very small. Think about that for a moment. The entire visible light output of a star comes from its full surface, a sphere that might be 1,000,000 kilometers across, or several million if it's a giant. The light comes from everywhere across that broad, burning face. But in an X-ray binary, the X-ray light comes from the innermost region of the accretion disk, a zone perhaps just a few hundred kilometers across, perhaps smaller. Around a neutron star, which is itself only about 20 kilometers wide, the X-ray emitting zone is tiny on any scale you'd care to use. The size of a city, the size of a small patch of countryside, and this changes everything. Because here is the geometry. When a planet transits an ordinary star, blocks its light as it passes in front, the star is millions of kilometers across. The planet might be 100,000 kilometers wide if it's a giant. So the planet covers perhaps 1% of the star's face. The other 99% of the star's light still reaches you. 1% dimming. But when something passes in front of an X-ray binary's compact emitting region, the ratio is completely different. If the emitting region is just a few hundred kilometers across, and the passing body is a Saturn-sized planet, roughly 100,000 kilometers in diameter, then the planet is not covering 1% of the source. It is covering the whole thing. It is larger by a tremendous factor than the thing it's blocking. It would blot it out completely. Not 1% dimmer, 0. Entirely dark. 100%. The light doesn't flinch. It disappears. And a disappearance, a source going from full brightness to nothing, is detectable even across 28 million light-years. Because the question is no longer, is this 1% dimmer than it was? Which is nearly impossible to confirm across such a distance. The question is simply, is it on or is it off? And that is a question our instruments can answer. That is the trick. Not better instruments, not bigger mirrors, not more sensitivity, a completely different geometry, a tiny lamp and a large shadow. The planet wins not by being seen, but by blotting out something small enough to blot. The specific source in M51 where this was observed belongs to a category called ultraluminous X-ray sources. ULXs, astronomers call them. These are among the most extreme X-ray emitters known, extraordinarily bright, too bright for a single stellar mass neutron star by the classical understanding, though our picture of what ULXs are has evolved and is still evolving. Some are thought to involve neutron stars in unexpectedly exotic accretion states. Some may involve black holes of intermediate mass. The one designated M51ULS1 is one of the brightest such sources in the Whirlpool, a pinpoint of fierce X-ray energy burning within that stunning spiral. And it was exactly the right kind of source to reveal what passed in front of it. The instrument watching all of this was NASA's Chandra X-ray Observatory. Chandra launched in 1999, and it is one of the great achievements of space astronomy, one of those instruments that, once you understand what it does, seems almost impossibly capable. It is NASA's flagship X-ray telescope, placed into a highly elliptical orbit that carries it far above Earth's atmosphere, because X-rays are absorbed by our atmosphere and simply cannot be observed from the ground. Chandra is sensitive, precise, and capable of resolving individual X-ray sources within other galaxies, which is exactly the capability that made this discovery possible. The Whirlpool galaxy, 28 million light-years away, contains many X-ray sources. Chandra can see them individually. It can watch them over time. It can notice when one of them changes. ESA's XMM Newton, another orbiting X-ray observatory, contributed corroborating data. XMM Newton and Chandra see the sky with different sensitivities and characteristics, and when two independent instruments tell a consistent story, the story becomes harder to dismiss. The team that analyzed all of this, that put together the careful, painstaking case for what the data might mean, was led by Rosanne DiStefano, an astronomer at the Harvard-Smithsonian Center for Astrophysics. This is one of the great centers of astronomical research, an institution responsible for an extraordinary breadth of discovery over the decades, and DiStefano brought to this problem a combination of theoretical creativity and exacting rigor. The paper reporting the candidate was published in September 2021 in Nature Astronomy, and the title itself was careful. It referred to an X-ray transit, a possible planetary transit in an external galaxy. The language was precise, measured, the kind of language that serious science uses when it is offering a strong and fascinating possibility without claiming more certainty than the data allows. The paper describes in its methodical way what the data showed. While monitoring M51ULS1, Chandra observed the X-ray brightness of the source undergo a remarkable change. It fell substantially. It fell over the course of roughly 3 hours to essentially undetectable levels, a total or near total eclipse of the X-ray source, and then, after those 3 hours had passed, it recovered. The brightness returned. The source came back, as if someone had briefly covered it with a hand and then moved the hand away. 3 hours of silence where there had been light. Now X-ray sources vary. They're not perfectly steady candles. Compact objects in violent feeding frenzies are not known for their placid reliability. So the first question the team had to answer was, could this dip just be the source varying on its own? A natural flicker in the infalling gas? A temporary disruption in the accretion flow? The shape of the dip argued against that. Natural variability in X-ray binaries tends to be irregular. It rises and falls in patterns that reflect the chaotic dynamics of infalling material. What the team saw here was symmetric. It went down and it came back up in a way that was consistent with something crossing in front of the source. An occulting body following a curved path, entering, covering, then exiting on the other side. The silhouette reading. The signature of a crossing. But there was another candidate explanation that deserved serious attention. Clouds. Space is not empty. Even within a galaxy between the stars there is gas, there is dust. Clouds of material, denser in some places than others, sometimes passing in front of a distant source and dimming it. If a dense cloud of gas or dust drifted across our line of sight to M51 ULS1, could it produce a dip like this? It could produce a dip. But the team found a way to argue against it. X-rays, like all light, come in different energies. High-energy X-rays are more penetrating than low-energy ones. They pass through material more easily. When a gas or dust cloud absorbs or scatters X-ray light, it does so unequally. The lower-energy X-rays get blocked more efficiently. The higher-energy ones pass through more easily. The cloud leaves a color fingerprint. The dimming it causes is chromatic. It changes the energy distribution of what comes through. A solid body, on the other hand, simply blocks what it covers. Every X-ray in its path, high energy and low energy alike, encounters an impenetrable physical barrier and goes nowhere. The dimming is achromatic, the same at every energy, as if the source was simply switched off. No color change, just darkness. What the Chandra data showed was achromatic dimming. Gray in the language that astronomers sometimes use for this kind of analysis. The X-ray spectrum did not shift. There was no evidence of energy-dependent absorption. The source did not become red or blue in X-rays. It simply went dark. Uniformly. Completely. A cloud would leave a signature. This left none. That achromaticity was the key diagnostic. Combined with the symmetric shape of the light curve, consistent with something physically crossing the source in a smooth orbital path, and combined with the total nature of the eclipse, Di Stefano and her colleagues built the case for a solid body, an object of planetary scale, roughly the size of Saturn, orbiting in this distant system and passing, from our perspective, directly in front of the tiny X-ray emitting heart of M51 ULS1. Let that image settle gently for a moment. A planet, roughly Saturn-sized, perhaps ringed, perhaps not, we don't know, perhaps barren, perhaps something stranger, orbiting, it seems, at a distance of tens of astronomical units from its host. An astronomical unit being the distance from the Earth to the Sun, about 150 million kilometers. Tens of those. Farther from its host than Saturn is from our Sun by the estimates that are possible to make from a single transit. With an orbital period possibly measured in decades, a year on this world might be longer than a human lifetime. And that brings us to the haunting part. The part that sits quietly at the center of this story like an unanswered letter. We saw the transit once, one crossing, 3 hours of eclipse in the archival and new Chandra data. One event. And because we saw it only once, we can't do what we'd normally do to confirm a planetary detection, wait for it to come around again. With exoplanets in our galaxy, confirmation typically involves watching the same periodic dip repeat, once, twice, 3 times, building a statistical case that this is real, that it is regular, that it is a planet in a predictable orbit. For M51 ULS1b, if it is real, the orbit is so large, the year so long, that the next transit, the next time this planet would cross in front of the source as seen from Earth, would not occur for approximately 70 years. 70 years! No astronomer alive today who was actively involved in this discovery will likely be alive to see the confirmation. Even the youngest graduate students in the collaboration if they are fortunate and healthy and still working in astronomy, would be very elderly people before they could train a telescope on M51 ULS-1 and watch the light go dark again and say, yes, here it is, the second pass, the confirmation, the certainty. There is something deeply human about that, a discovery that cannot be confirmed within a career. A question answered once, provisionally, and then handed forward to people not yet born. It is the long patience of science extended to its most poignant limit. And so the community holds M51 ULS-1b as a candidate, a strong candidate, a genuinely compelling one, with an honest and specific case made for it, with alternative explanations carefully considered and argued against. But not a confirmed planet, not yet, perhaps not in our lifetimes. Rosanne Di Stefano and her team were clear about this. The paper was honest about it. This is how careful science works. You present what you found, you make the strongest case you can, you acknowledge what you cannot yet know, and you let the record stand waiting for the future. It is one of the things that makes science trustworthy. Not that it claims certainty, but that it knows precisely where certainty ends and the open question begins. So we have a candidate, found by a disappearance, in a system that is itself one of the most extreme environments in the Whirlpool galaxy, because the host of this candidate planet, the thing it orbits, is not a sun. Not in any sense we would normally use that word. Our sun is a middle-aged, medium-sized star, steady and relatively calm, burning hydrogen in its core, warming its planets with golden, visible light. The thing M51 ULS-1b might orbit, if it orbits anything at all, is none of those things. It is a dead star, or more precisely, it is the aftermath of a star's death, still violently active in the way that only dead things can be when they are being fed. A neutron star or a black hole, the two candidates for the compact object at the center of M51 ULS-1. Both of these are what you get when a massive star, much more massive than our sun, runs out of fuel, collapses inward under its own gravity, and then explodes in one of the most energetic events in the universe, a supernova. The outer layers of the star are blasted away into space in a flash of light that can briefly outshine an entire galaxy, and the core is compressed beyond any ordinary physical intuition into something extraordinary. If the star was massive but not too massive, the core becomes a neutron star, a sphere roughly 20 kilometers across, the width of a city, in which the mass of more than our entire sun is packed so tightly that the interior is essentially a single, enormous atomic nucleus. A teaspoon of neutron star material would weigh hundreds of millions of tons. It rotates rapidly, it has a ferociously strong magnetic field, and it radiates in X-rays, in radio waves, in ways that depend on exactly how it is feeding and spinning. If the star was more massive still, the core becomes a stellar mass black hole, a region of space where gravity has overcome everything, where the collapse has continued past the neutron star stage, where the density is effectively infinite at the singularity and where even light cannot escape from within a certain distance, the event horizon. Either way, what remains is something unimaginably compact and energetic. And in M51 ULS-1, whatever that compact remnant is, it has a companion, a large, luminous, still-living star, the kind of hot, blue-white giant that burns brilliantly, but briefly. That star's outer layers drift off into space, and the compact object's gravity catches that drifting material, drags it down, heats it to tens of millions of degrees, and produces the fierce, city-wide X-ray glow that Chandra could see across 28 million light-years. The candidate planet, M51 ULS-1b, orbits this system, the wreckage of an explosion, a stellar corpse and its brilliant but doomed companion. This world has already lived through the death of at least one star. The supernova that created the compact object happened, presumably, long before the planet was where it is now. Either the planet survived the explosion and migrated outward, or it formed later from material thrown off by the cataclysm. The details of how a planet could exist in such a system are themselves unresolved. That is perhaps a question for another night. But what is clear is this: if M51ULS1b is a planet, it orbits one of the most violent places in its galaxy. It circles the aftermath of stellar death, bathed in X-rays rather than sunlight, tracing a lonely path at tens of astronomical units from a system so extreme that its X-ray glow outshines many entire galaxies in those specific wavelengths. And it was precisely because of that extreme glow, that fierce, compact, city-sized X-ray heartbeat, that a Saturn-sized planet could pass in front of it and leave a shadow we could see from here. The violence is the signal. The extremity is what made it visible. And all of this, the dead star, the infalling matter, the X-ray glow, the orbital mechanics that brought a planet across our line of sight at exactly the moment Chandra happened to be watching, all of this happened inside a galaxy that from here looks so purely, so improbably beautiful that for generations it was simply called the most photogenic spiral in the sky. That is the thread we'll follow next, the Whirlpool itself. Because the story of M51's elegance and the story of M51's violence are, it turns out, the same story, told from two different angles. And the connection between them, the way the galaxy's famous beauty is literally created by the same catastrophic forces that built the extreme system hiding a possible planet, is the part that most people who point a camera at M51 and say, "Isn't it lovely?" have never quite paused to consider. But that, as I said, we'll come to in just a little while. There's no rush. We have the whole night. For now, let it be enough to hold what we've covered, the clever geometry of a tiny source and a large shadow, the instrument that watched, the team that interpreted, the candidate that may be the first world ever found outside our galaxy, and the haunting, patient uncertainty of a confirmation that lies perhaps 70 years away. So let's slow down here and take apart exactly how the trick works, because the detection mechanism is, in some ways, more beautiful than the discovery itself. And understanding it is what makes the discovery feel real rather than miraculous. You've seen a planet transit before, at least in description if not in person. A planet crosses in front of its star. The star's light dims slightly, measurably, briefly. The Kepler Space Telescope found thousands of planets this way, watching stars blink and flutter over years, cataloguing the tiny rhythmic dips in brightness that meant something was passing, again and again, between us and the star. Tiny is the operative word. When a planet like Jupiter, the biggest planet in our solar system, crosses in front of our Sun, it blocks about 1% of the Sun's light. Earth blocks 1/10 of that, 1/10 of 1%, a whisper, a shimmer. And that's Jupiter and Earth transiting our own star, whose light arrives here crisp and concentrated after traveling a mere 8 light minutes. Now take that same planet and move it 28 million light years away. The star's light, already diluted across that unthinkable distance, arrives at our instruments as the faintest possible signal. A 1% dip in that signal, or 1/10%, is not just difficult to detect, it is, in any practical sense, invisible. Drowned in noise, swallowed by the ordinary fluctuations of distance and atmosphere and instrument sensitivity, you could stare at that star for a century with the finest optical telescope ever built, and you would never catch a planet's shadow in it. This is why, in the entire history of planet hunting, every confirmed exoplanet, every single one in that catalogue of 5,000 and counting, has been found inside the Milky Way. Most of them within a few thousand light years. close enough in cosmic terms that the stars still shine with enough coherent brightness for a planet's crossing to leave a readable mark. Reach outside the galaxy, and that method closes. The door shuts, the signal disappears into the dark, unless you change the light source entirely. And that is what Rosanna Di Stefano and her colleagues at the Harvard-Smithsonian Center for Astrophysics realized, or rather formalized into a workable observational strategy. Instead of watching a normal star, a broad, blazing disk whose light comes from a surface millions of kilometers wide, you watch an X-ray binary. And the physics of what an X-ray binary actually is changes everything about what a planet can do to it. Here is what an X-ray binary is, said plainly. Two objects in orbit around each other. One is a massive star, often a blue supergiant, burning hot and fast, pouring its outer layers into space. The other is a compact remnant, a neutron star, or a stellar mass black hole, the collapsed core of a star that already exploded as a supernova sometime in the past. The compact object's gravity is so intense that it pulls streams of gas from its companion. That gas spirals inward, forming an accretion disk, a whirlpool of matter falling toward the point of no return. And as it falls, it heats to temperatures of millions of degrees, not thousands, millions. And matter at those temperatures doesn't glow in visible light. It glows in X-rays. Now here is the crucial part. The region where those X-rays are actually produced, the innermost part of the accretion disk right at the edge of the neutron star's surface or the black hole's event horizon, is tiny. Not tiny in the way a marble is tiny. Tiny in the way that it is, in some cases, no larger than a city. Certainly no larger than a planet. We're talking about a light-emitting region that could, if the geometry is right, be completely covered by a Saturn-sized body passing in front of it. Completely, fully, 100%, not a 1% dip, not a 0.1%, not a shimmer in the noise. The X-ray signal goes to zero, off, dark. And then, as the transiting object continues along its orbit, the source comes back, returning to its previous brightness, clean and symmetric on either side of the eclipse. This is a different kind of transit. It's not a planet dimming a star's light by a tiny fraction. It's a planet switching off an X-ray beacon. And that switch, that total extinction, is exactly the kind of signal that can be detected across 28 million light-years, because the change isn't a fraction of a percent embedded in noise. It's the difference between bright and gone. The violence is doing the geometry for you. A compact object is small enough to be covered. A normal star is not. And so the very extremity of the system, the collapsed star, the infalling matter, the X-ray furnace at the center, is what opens the window. You cannot find a planet around a normal star at this distance. But a planet around a dead star in a system violent enough to produce ultraluminous X-rays is at least theoretically findable. The door that was closed opens just a crack in a different part of the spectrum. And this is what the specific source in M51 is. It's classified as an ultraluminous X-ray source, a ULX. These are among the brightest compact object systems known. The name is literal. They emit X-rays at luminosities so extreme they exceed what physicists once thought was the theoretical upper limit for a single accreting object. There are various explanations for why they can be so bright: the geometry of emission, the mass of the compact object, the rate of accretion. But the relevant point for our purposes is that a ULX is bright enough to be individually monitored in another galaxy, which is exactly what Chandra can do. NASA's Chandra X-ray Observatory, launched in 1999, was built for precisely this kind of work. It operates above Earth's atmosphere, which is fortunate, because our atmosphere absorbs X-rays almost completely, which is one reason the universe's X-ray glow was invisible to us until we put instruments in space. Chandra's angular resolution, its ability to separate individual point sources in a crowded field, is extraordinarily fine for an X-ray telescope. It can look at a galaxy like M51 and isolate single binary systems within it, track their brightness over time, and notice when something changes. That is what the team did. They searched archived Chandra observations of M51, looking at the light curves of known X-ray sources or to the records of brightness over time, and in one of them, the ULX designated M51 ULS1, they found it. A dip, beginning, deepening, reaching what appeared to be complete extinction, and then recovering, all over the course of roughly 3 hours. Symmetric, total. Unlike anything a random fluctuation in the source itself would naturally produce. ESA's XMM Newton, Europe's own X-ray space telescope, provided corroborating observations that helped contextualize the data. But the interpretation was always going to require argument, because a dip in an X-ray light curve could have explanations other than a planet. The most obvious competing explanation is a cloud of gas or dust passing in front of the source. Interstellar material absorbs X-rays too. A cloud crossing the line of sight could, in principle, produce a dip. Here is where the physics does its most satisfying work. Gas and dust don't absorb all X-ray energies equally. Higher energy X-rays, harder X-rays in the jargon, penetrate more easily than lower energy, softer ones. So if a gas cloud dims an X-ray source, it does so in a specific way. The color of the emission changes. The ratio of soft to hard X-rays shifts. The eclipse isn't gray, it has a spectral fingerprint. The dip observed in M51 ULS1 didn't show that fingerprint. The dimming was achromatic, gray, in the sense that it affected all observed energies in the same proportional way. That's the signature of a solid, opaque object, blocking the source completely, not a semi-transparent cloud filtering it. A planet, or something of planetary scale, dense and solid, would produce exactly that clean, grey, total eclipse. A gas cloud almost certainly would not. This is the argument Di Stefano and colleagues made in their 2021 paper in Nature Astronomy. Not just we saw a dip. The detailed case, here is the dip, here is its shape, here is the achromatic character of the extinction, here is why a gas cloud is unlikely, here is why the natural variability of the source is unlikely, here is the size of the transiting object implied by the geometry, roughly Saturn-sized, and here is the orbital distance implied by what we know of the system, somewhere in the range of tens of astronomical units farther from its host than Earth is from our Sun, perhaps farther than Saturn is from ours. The candidate was given a designation M51 ULS1b. The B in exoplanet naming conventions means it orbits the primary of the system, the compact object, or perhaps the binary as a whole. A world named in the catalogue of things humanity has found, provisionally, pending confirmation, that has its own haunting timeline. And that timeline is worth sitting with for a moment because it's one of the stranger features of this discovery. If the planet is real and if the orbital distance estimates are approximately correct, then M51 ULS1b takes a very long time to complete one orbit around its host. The implied orbital period is measured not in months or years, but in decades, possibly longer. The team calculated that the next time the planet would transit the X-ray source, if the geometry aligned again, would be roughly 70 years from now. 70 years. That's not a follow-up observation you can schedule for next autumn. That's not a career. That's a generation. So the discovery sits right now in this strange suspension, a dip in an X-ray light curve, a set of arguments, a designation in a catalogue, and a next opportunity to test any of it that falls somewhere around the year 2091. There's something quietly humbling about that number, 2091, a year that feels almost fictional from where we stand, the kind of date that turns up in science fiction as shorthand for the remote future. And yet that's the rough arithmetic of the situation. If M51 ULS1b is real, if its orbit is roughly what the geometry implies, then the next transit would happen in a time frame that exceeds most human lifetimes. The astronomers who found it will not, in all likelihood, live to see it confirmed. Their students might not either. This is one of the genuinely strange things about working at the frontier of astronomy. Confirmation, in the ordinary sense, run the experiment again, reproduce the result, is not always available. The universe does not rearrange itself for our convenience. It keeps its own schedule, and when an orbit is measured in decades, the scientific standard of repeat the observation runs headlong into the simple biological fact that we are not that patient by nature, and that careers and lives have a different time scale than orbital mechanics. So you might reasonably ask, how then does science deal with this? How do you hold a result that you cannot recheck on any practical timeline? You do what Di Stefano and her colleagues did. You build the case with what you have. You lay out every alternative explanation you can think of, and you work through each one carefully, and you show your reasoning for why the one that remains, a planet, is the most consistent with the data. Not proven, consistent. And you are honest about the difference. That honesty is, I think, one of the most underrated qualities in scientific writing. It would have been very tempting, given the magnitude of what this result would mean, the first planet ever found outside the Milky Way, to soften the caveats, to lean into the headline, to let the excitement carry the language somewhere beyond what the data strictly supports. And to their credit, the team did not do that. The language in the paper is careful. It is hedged in exactly the right places. It says candidate, it says consistent with, it explains the 70-year problem openly. And so what we are left with is not a confirmed discovery exactly. It is something perhaps more interesting, a very well-reasoned argument that something extraordinary is probably there, combined with an admission that we cannot, right now, close the loop. Let's stay with that loop a little longer because it rewards the patience. The most important piece of the argument, the piece that does the heaviest work, is the character of the eclipse itself. Not just that there was a dip. Lots of things cause dips in X-ray light curves. X-ray sources are variable by nature. Compact objects undergoing accretion are famously, sometimes furiously, unsteady. They flare, they flicker. They have episodes of enhanced brightness and periods of relative quiet. A dip on its own is not remarkable. What made this dip worth arguing about was its shape, its duration, and most critically, its color. Let me explain what I mean by color, because it's the crux of the argument. When X-rays travel through gas or dust, they don't all behave the same way. Lower energy X-rays, indeed the softer end of the spectrum, are more easily absorbed. Higher energy X-rays cut through more freely. So if a cloud of gas or dust passes in front of an X-ray source, you expect to see what's called energy-dependent absorption. The soft X-rays disappear first and most completely, while the hard X-rays are dimmed less. The cloud leaves a fingerprint in the spectrum. It changes the color of the light, or more precisely, it changes the ratio of soft to hard photons that reach you. Astronomers call this a spectral change. If, on the other hand, something solid and opaque passes in front of the source, something with a well-defined edge and no significant atmosphere, something roughly planetary in scale, then it simply blocks the light. All of it, equally. It doesn't preferentially absorb the soft end or transmit the hard end. It just covers the source the way your hand covers a lamp. The spectrum of whatever light leaks around the edges stays the same. What changes is simply the total amount reaching you. That latter case, where the dimming is equal across all energies, where the spectrum doesn't shift, where the extinction is grey in this technical sense, is called an achromatic eclipse. And that is what the Chandra data showed. The dip was achromatic. During the roughly 3 hours when the X-ray flux fell to essentially undetectable levels, there was no energy-dependent signature of the kind you'd expect from an intervening gas or dust cloud. The dimming was uniform. The source went dark in a way that is consistent with something solid, something opaque, something with a well-defined boundary simply passing in front of it. That is a very particular kind of eclipse, and it is not what you'd expect from a cloud. Now clouds are not impossible to rule out entirely from a single observation. Astronomers know that some dense, compact clumps of material can produce achromatic-looking absorptions under the right conditions. This is one of the reasons the community received the result with genuine interest, but also genuine caution. But the combination of factors, the total extinction, the symmetrical shape of the dip, the 3-hour duration, the achromatic character, the specific system involved, all of these together form a coherent picture that a planet fits better than a cloud does. Imagine for a moment trying to construct a cloud that would do this. It would need to be compact enough to fully cover the X-ray emitting region without any spectral signature. It would need to arrive and depart on a smooth, symmetric timescale consistent with a transiting object moving across a small source. It would need to not leave any obvious residual signal in the wings of the eclipse. This is not impossible, but it requires a set of conditions that are, to put it mildly, somewhat contrived. The planet hypothesis doesn't require any special pleading. It requires only that you accept the ordinary physics of a large opaque object blocking a small, luminous one. Occam's razor, as ever, points in a direction. It doesn't close the case, but it points. There is also the question of the source's own natural variability. Ultraluminous X-ray sources, we should spend a moment with them because they are remarkable in their own right, are not quiet, well-behaved systems. They are among the most energetic compact object binaries known, shining with X-ray luminosities far beyond what a single stellar mass object ought to be able to produce at face value. They are bright, and they are often variable. So one explanation for the dip is simply that the source itself quieted down for 3 hours. These things happen. The accretion flow feeding the compact object can change. The inner disk can shift. The geometry of the system can evolve on short timescales, producing luminosity drops that look, superficially, like something blocking the source. The team considered this. They looked at the behavior of the source before and after the dip, at its long-term light curve, at what was known about the variability habits of systems like this one. And while they could not rule out source variability with absolute certainty, the kind of absolute certainty is not on offer here. The character of the dip was not typical of the kind of variability these systems usually show. Intrinsic variability tends to be less symmetric, less total, less sharp-edged than what an external occultation would produce. The dip in M51 ULS1b's light curve had the geometry of a transit. It looked like something going in front, not something switching off from within. Again, not proof. An argument, a careful, layered argument built from the shape of the data, and so the candidacy holds. M51 ULS1b remains what it was when it was announced, a candidate designated, named, placed in the catalogue of things humanity has noticed, waiting for the kind of confirmation that won't arrive for the better part of a human lifetime. What does that mean practically? It means this: the science moves forward anyway. One of the great clarifications that this discovery prompted, regardless of whether the planet turns out to be real, is an opening of perspective about what is possible to detect and where. If you can catch a planet's shadow in M51, what else might you catch in the Chandra archive? The archive is large. It contains decades of X-ray observations of galaxies near and moderately far, searches of that archive for similar events. Total, achromatic, symmetric dips in the light curves of ultraluminous X-ray sources in other galaxies are exactly the kind of work that opens a new branch of investigation. The method, if it works, is replicable, not on a single source basis in the way that a radial velocity survey is replicable, but as a statistical approach, watch many X-ray binaries in many nearby galaxies over many years and look for these events. The extraordinary thing is that this is now a real research program, not a hypothetical, not a distant aspiration. A research program that exists because one team looked at one light curve in one galaxy and thought, wait, what is that? And here is where the two spines of this story, the planet and the galaxy it lives in, begin to twist together more tightly. Because you might wonder, why M51? Of all the galaxies in the sky, why is this the one where a candidate planet has turned up in the X-ray data? Why this particular system, this particular galaxy? The answer is not a coincidence exactly, it is more like a consequence. M51 is a face-on grand design spiral at a distance of roughly 28 million light-years, and it is exquisitely well studied. It has been observed by Chandra many times. It has a large, well-characterized population of X-ray sources, including a healthy number of ultraluminous X-ray sources, heading the exact kind of systems whose tiny emitting regions make the transit technique possible. And the reason M51 has so many of these extreme systems is, at least partly, the reason M51 looks the way it does. This is where we need to talk about what M51 actually is. Not the postcard, the physics. When you look at a photograph of the Whirlpool galaxy, what you see is one of the most striking images in the sky. It is the quintessential grand design spiral, two long, sweeping arms, well-defined, nearly symmetrical, pinwheeling outward from a bright central nucleus. The arms are lit with the blue-white shimmer of young, hot stars. There are pink knots of ionized hydrogen along the edges. Stellar nurseries, caught in the act of birth. It is clean. It is organized. It is the galaxy you would draw if someone asked you to draw a galaxy. But notice something in any photograph you've seen of it. There is a companion. A smaller, denser, pinkish-orange blob sitting at the tip of one of those graceful arms, connected by a luminous bridge of stars and gas, looking almost like an afterthought, a bead on a thread, but very much there. That is NGC 5195, and it is not an afterthought. It is the reason. Charles Messier catalogued M51 in 1773. He was sweeping the sky, looking for comets, keeping a list of fuzzy objects that weren't comets. A nuisance list, really, meant to stop him from being confused. And M51 ended up in it. Number 51, a faint smudge in the constellation Canes Venatici, just off the handle of the Big Dipper. He noted that there seemed to be two of them. He didn't know what they were. More than 70 years later, in 1845, a man named William Parsons, the third Earl of Ross, an Irish astronomer of considerable means and considerable ambition, pointed a telescope at M51 that was at the time the largest in the world. He'd had it built on the grounds of Birr Castle, in County Offaly, in the middle of Ireland, which is not a place renowned for its clear nights. He called it the Leviathan of Parsonstown, which is exactly what a 72-inch reflecting telescope built by a Victorian aristocrat should be called. And through the Leviathan, in 1845, Lord Rosse saw something that nobody had ever seen before. He made a sketch, and the sketch showed a spiral. Not a blur, not a smudge, a spiral. Arms curling outward from a central nucleus, like a pinwheel, like water going down a drain, like something alive and turning. It was the first time anyone had ever recognized spiral structure in another galaxy. Though of course they didn't call it a galaxy then, they called it a nebula. The nature of these objects and the fact that they were themselves vast, distant systems of hundreds of billions of stars would not be understood for another 80 years. But Lord Rosse saw the shape, and the shape, as we now know, is not an accident. The spiral arms of M51 are there because of NGC 5195. The two galaxies are in the middle of an interaction, a collision in slow motion, playing out over hundreds of millions of years. NGC 5195, the smaller companion, has been passing through and around M51's disk, its gravity tugging at the stars and gas and dark matter of the larger system, sending waves through the disk the way a hand, dragged through still water, sends ripples outward from the disturbance. Those ripples are the arms. More precisely, the interaction with NGC 5195 excites and amplifies what are called density waves in M51's disk. Density waves are a beautiful piece of physics. They are not material waves, i.e. the stars and gas do not travel outward with the arms. Instead, the arms are like a traffic jam on a highway. The jam stays in one place while the individual cars move through it, slowing as they enter and accelerating as they leave. The pattern persists even as the material rotates through it. In a galaxy like M51, the arms are regions of slightly enhanced density moving through the disk as waves. As gas and dust flow into an arm, compressed by the wave, the density rises high enough to trigger gravitational collapse. The gas fragments, clumps form, protostars ignite. The arm lights up with new stars, most of them hot, short-lived, and brilliant, which is why the arms are blue, white, and pink rather than the yellower, older light of the central nucleus. Star formation follows the arms the way wheat follows the rain. And the compression that drives the star formation is not random. It is driven, at least partly, by the companion's gravitational pull. NGC 5195 is the engine behind the beauty. The collision sharpens the spiral, the cannibalism makes the art. Now, stars that form quickly in dense regions under extreme conditions tend toward the massive end of the distribution. Massive stars are profligate with their fuel. They burn bright and they die young on timescales of millions of years rather than billions. And when massive stars die, they die dramatically. As supernovae, the catastrophic collapses that can, if the mass and the physics cooperate, leave behind compact remnants, neutron stars, or stellar mass black holes. This is the thread that ties the galaxy's beauty to the planet's discovery. M51, because of its ongoing interaction with NGC 5195, has enhanced star formation in its arms. That enhanced star formation produces massive stars at a higher rate. Those massive stars die as supernovae at a higher rate. Those supernovae leave behind neutron stars and black holes at a higher rate. And those neutron stars and black holes, if they find themselves in binary systems with surviving companion stars, can begin accreting material and become X-ray binaries. And the most extreme of those become ultraluminous X-ray sources. M51 has more ultraluminous X-ray sources than a quieter, more isolated galaxy of similar size would. And M51 ULS-1, the specific source where the candidate planet's transit was detected, is one of them. So the collision gave us the arms, and the arms gave us the massive stars, and the massive stars gave us the dead stars, and the dead stars gave us the X-ray sources, and the X-ray sources precisely because they shine from a region so tiny that a planet can block them completely, gave us the detection. The most beautiful galaxy in the sky revealed what might be the most distant planet ever found, because it is, and has been for hundreds of millions of years, in the process of tearing itself apart. That is a thread worth following all the way to the end. Let's come back to the planet itself. You could to M51 ULS-1b as a world, as a place, as a thing that might exist, and sit with what it would actually be like. We don't know very much about it, and it's important to be clear about that. The data tells us a transit occurred. The shape and duration of the transit give us a rough size, something approximately Saturn's dimensions, a large, probably gaseous world of considerable girth. The orbital parameters implied by the system give us a rough distance from the host, tens of astronomical units, which is the scale of the outer solar system here. The cold and distant reaches where light from your star arrives as not much more than a bright point in a dark sky. And the nature of the host tells us something about the environment. That environment is extraordinary in a way that is difficult to fully convey. The host of M51 ULS-1b is not a star like our Sun. It is not even a dying star in the way that a red giant is dying, slowly, swelling, reddening over billions of years. The host compact object will be the neutron star, or black hole at the center of this system, is the remnant of a star that has already died. It has already gone through its entire stellar life cycle. It has already exploded. The supernova happened. The core collapsed. What is left is an object of tremendous density, either a neutron star spinning at enormous rates with a surface gravity millions of times Earth's, or a stellar mass black hole where nothing, not even light, escapes from within a certain radius. This compact object is now pulling material from a companion, a massive donor star, the kind of large, luminous, hot star that only lives for a few million years before it too will explode. The material falls inward, heating to millions of degrees, glowing furiously in X-rays. The inner region of this accretion disk, the part that actually emits the X-rays, is small, very small, comparable in scale, as we've said, to a planet. And if M51 ULS-1b orbits out at tens of astronomical units, it is circling this system from what is, on a stellar scale, a considerable distance. It is far enough out that its year is measured in decades, far enough out that the X-ray glow of the compact object's accretion, fierce as it is, arrives as a relatively distant light source, intensely energetic, bathing the planet in radiation of a kind that has no real analogy in our own solar system, but not necessarily so intense at that distance as to render the concept of orbiting meaningless. Whether such a world could have formed there, or whether it drifted there, or whether it survived the supernova that created the compact object, we genuinely do not know. Planets have been found orbiting neutron stars before. There is a famous case of planets found around a pulsar called PSR 1257+12, discovered in the early 1990s, which remains one of the strangest pieces of planetary science on record. Those worlds are thought to have formed from the debris of the supernova itself, or from material shed during the stellar death and later reaccreted into a disk. It is possible, maybe even likely, that something similar could happen in a system like M51 ULS-1b's host. Or it is possible the planet was there before, that it orbited the progenitor star, the massive star that eventually exploded at a great enough distance that when the explosion happened, when the outer layers were blasted away and the core collapsed, the planet was not destroyed. Supernovae are violent, but they are not omnidirectional walls of annihilation at every distance. A planet orbiting far enough out might, if the geometry were right, survive. We don't know which story is the true one here. The data doesn't reach that far. What we know is that something the size of Saturn appears to have crossed in front of an X-ray source in the Whirlpool galaxy for about 3 hours, and that the most coherent interpretation of that fact is a planet. A planet circling a dead star in a galaxy 28 million light-years away. The strangeness of that accumulates the longer you sit with it. And this brings us back to the honesty problem, the place where the science has to be careful and where the popular presentation of this discovery has sometimes been less careful than it should. M51 ULS-1b is a candidate. That word carries real weight. It is not a formality, not a bureaucratic hedge, not the scientists being modest for the sake of modesty. It reflects a genuine epistemic situation. The evidence is suggestive, the argument is coherent, but the confirmation that would make this unambiguous, a second transit, preferably observed by multiple instruments with the full geometric and spectral detail that would cement the identification, is not available. Not now. Not for a very long time. The 70-year figure is not a precise prediction. It is an estimate based on the implied orbital period, which is itself estimated from the orbital distance, which is itself inferred from what we know of the system. The uncertainty compounds. The next transit might come sooner, it might come later. The geometry might not align perfectly. Future observers, living and working in a world 70 years from now with instruments we cannot yet imagine, will be the ones who have the opportunity to either confirm or quietly retire this result. There is something almost moving about that. Science is not just a practice of individuals or careers or even generations. It is a practice of centuries. The people who set up this observation, who analyzed this data, who wrote this paper, are handing something forward, a question, an unresolved thread, a loose end in the catalogue of what we know, to people who haven't been born yet. The 70-year wait is not a failure of the discovery. It is a feature of the kind of science that gets done at the true frontier, where the questions outrun the tools available to answer them. And in the meantime, the archive remains. All those X-ray observations of all those nearby galaxies stacked up over Chandra's lifetime since 1999, waiting to be searched, looking for other dips, other shadows, other moments where a planet somewhere out there in the cosmos far beyond our own spiral arm slipped between us and a dying star and left a 3-hour signature in the data. The method works, or at least the physics says it should work, and the M51 ULS-1b case is the demonstration that nature cooperates, at least sometimes. So the question that opens now is not just, is M51 ULS-1b real, but something much larger. If planets exist in other galaxies, and there is no particular reason they shouldn't, galaxies are full of stars, and stars form planets as a matter of routine. Then how many of them are out there, entirely unreachable by any method except this one? How many worlds are there, beyond the boundary of the Milky Way, orbiting their own suns or their own dead stars, drifting through their own galactic arms? We cannot see them directly. We cannot detect the slight wobble they induce in their host stars because the wobble is far too small across that distance. We cannot watch them transit in visible light because the fraction of a star's disk they'd block is a fraction of a percent, and that fraction of a percent of a star's light, already reduced to virtually nothing by the inverse square law over 28 million light-years, is indistinguishable from the noise in our best optical instruments. But if the host is a tiny, fierce X-ray source, and if the planet is large enough, and if the geometry aligns, and if we are watching, then the shadow is real, and the shadow is catchable. That is the window. Narrow, difficult, dependent on a specific and somewhat exotic class of host system, but real. And once a window opens in astronomy, people look through it. So the story of M51 ULS-1b is not only the story of one candidate in one galaxy, it is the opening of a question. Are there extragalactic planets that we could, with the right observations and the right patience, detect? And if so, what would it mean for our picture of the universe? A universe in which stars and planets are not just a Milky Way phenomenon, not just something our particular island of stars does, but something that every galaxy does, every collection of hundreds of billions of suns, from here to the edge of what we can see? The answer, almost certainly, is yes. Galaxies are full of stars. Stars make planets. That process does not appear to require anything special about our galaxy. The physics of protoplanetary disks and gravitational accretion is chemistry and physics, not local custom. But knowing that and demonstrating it are different things. Up until September 2021, every planet we had ever found, every single one of the more than 5,000 confirmed exoplanets in the catalogue, was a local resident, a Milky Way citizen, something that lives in the same spiral arm neighborhood, cosmically speaking, as us. M51 ULS-1b, if it is real, would be the first exception. The first confirmed, or candidate to be precise, always candidate, resident of another galaxy, the first world beyond the river of light overhead. And it was found not because we could see it shining, not because we could measure the gravity it pulled on its host, but because it crossed in front of a dying star's death glow for 3 hours one day, and we happened to be looking, and Chandra happened to be on. And a team led by Rosanna Di Stefano happened to look at the data and recognize the shape of what they were seeing. 3 hours. 28 million light years. A shadow cast by a Saturn-sized world on an X-ray source smaller than a city. That is the detection. That is the scale of it. And it happened in the Whirlpool, in the most photographed, most studied, most visually celebrated spiral galaxy in the sky. The one that looks like what a galaxy is supposed to look like, right down to the clean arms and the bright nucleus, the one that has been hanging on observatory walls and in astronomy textbooks for 150 years. The one that Charles Messier noted in his comet nuisance list in 1773, that Lord Rosse sketched through a telescope the size of a city bus in 1845, that has been returned to again and again by generations of astronomers who found in it a kind of perfect, paradigmatic beauty. That beauty is a collision. The spiral is being made and sharpened by a gravitational interaction that has been ongoing for hundreds of millions of years, that will continue for hundreds of millions more, that will eventually fold NGC 5195 into M51's disk in the slow, inevitable arithmetic of galactic mergers. The arms are there because a smaller galaxy has been passing through the larger one. The star formation is enhanced because the gas is being compressed by that passage. The extreme star, the ones that live fast and die in supernovae, are more abundant because of it. And the X-ray binaries, the ultraluminous sources whose tiny emitting regions make the transit method possible, are there in part as a downstream consequence of all that gravitational violence. The perfect galaxy is a slow catastrophe. The first planet found outside the Milky Way was found there not despite the chaos, but because of it. So let's stay with that for a moment. The Whirlpool. If you have ever seen a photograph of it, and you probably have, because it appears in textbooks and on observatory posters and in popular science magazines almost as often as photographs of our own galaxy, you know what it looks like. It looks exactly like a galaxy is supposed to look. Two great curving arms sweeping out from a bright central nucleus, one of them reaching toward a smaller companion that sits at its tip like a pendant on a chain, clean, symmetrical, luminous. The kind of image that makes you feel, even from the safe distance of your bed or your couch or wherever you are right now, that the universe is organized, that it has a kind of design to it, a geometry that rewards the eye. There is a reason it has that quality. There is a reason it became the textbook galaxy, the one astronomers reach for when they want to show someone what a grand design spiral looks like. And that reason is not, it turns out, a simple one. It is not the story of a stable, quietly rotating pinwheel of stars drifting undisturbed through the dark. It is a story about violence, about collision, about the way that gravitational forces on an enormous scale can take chaos and, almost as a byproduct, produce something breathtaking. The Whirlpool M51, Messier 51, NGC 5194, it has all these names, and all of them point to the same object, about 28 million light-years away, in the constellation Canis Venatici, near the handle of the Big Dipper. It is face-on to us, meaning we see it nearly flat, spread out like a map of itself, which is part of why it photographs so well. The orientation is a gift. Most spiral galaxies we see at an angle or edge-on, so you get a thin sliver of light with a dark dust lane through the middle. M51 gives you the whole thing from above, laid out in full. Every arm, every dust lane, the companion at the end of the arm, all of it visible at once. Charles Messier was a French astronomer, and his life's work was comets. He loved comets, hunted them obsessively, catalogued their paths across the sky. But comets are faint smudges when they're far from the sun, and the night sky is full of other faint smudges that are easy to mistake for a comet if you don't know what you're looking at. Nebulae and star clusters and distant galaxies, all of them fuzzy and unresolved through an 18th century telescope. So Messier made a list of them, not because he was interested in them, not because he understood what they were. Most of them at that time nobody understood, but because they kept fooling him. He catalogued them as nuisances, obstacles, the things that were not comets. He stumbled across M51 in 1773, noted it, moved on. He could not have known that the smudge he was filing away as a comet decoy was a galaxy, 100 billion stars in a gravitational embrace, 28 million light-years from his eye. The telescope of the 18th century could resolve enough to see that something was there, but not enough to see what it was. Galaxies were not yet understood as separate, island universes of their own. The word galaxy, in the modern sense, a self-contained structure of billions of stars, utterly separate from the Milky Way, would not be confirmed until the 20th century. For Messier, it was just a faint blur. Number 51 on the list of blurs that were not comets. 72 years later, in 1845, a man named William Parsons pointed a different kind of telescope at M51 and saw something no one had seen before. William Parsons was the third Earl of Ross, an Irish nobleman and scientist with a passion for building the largest reflecting telescopes in the world. His greatest instrument was an enormous metal mirror, 6 feet across, about 2 meters, housed in a tube so large that it became known as the Leviathan of Parsonstown. Leviathan. The name gives you a sense of what it looked like to people who encountered it at the time. A massive, almost industrial structure set between 2 masonry walls on his estate in County Offaly, Ireland. It was, for several decades, the largest telescope in the world, and when Lord Ross turned the Leviathan toward M51, something resolved out of the blur, something curling. He made a sketch of it, careful and detailed, and what he drew were arms. Sweeping, curved arms spiraling outward from a bright center. He had seen spiral structure in what we now call a galaxy, the first time any human being had ever recorded such a thing. He did not know he was looking at another galaxy. That concept was still decades away from confirmation, but he drew what he saw, and what he saw was true. That sketch still exists. You can look at it. It is remarkably good given the instrument and the era, given that he was working with reflected light off a metal mirror in the damp Irish air, given that he had no photograph, no digital image, no accumulated exposure over hours, just a careful eye at the eyepiece and a hand that recorded what it found. The spiral is there in his drawing. The companion, NGC 5195, is there at the end of the arm. He didn't know what either of them was, not fully, but he saw them. And here is where the story of the Whirlpool's beauty becomes complicated. Because for a long time, the beauty was taken as a given. M51 is beautiful, and that is that. A grand design spiral, meaning a galaxy whose arms are prominent and well-defined and sweep around it cleanly. The kind of spiral you see in illustrations. Not all spirals are like this. Many are patchy, fragmented, wound loosely or unevenly. M51 has the quality of having been drawn by a careful hand. It looks intentional. But spiral arms in a galaxy are not permanent structures the way a wheel's spokes are permanent. They are not solid objects rotating together. They are density waves, regions of compressed gas and dust where stars are more tightly packed, where star formation is enhanced, where the material of the galaxy is caught momentarily in a kind of traffic jam. The wave sweeps through the disk the way a sound wave sweeps through air. The individual stars and clouds pass through it, slowing down, piling up, then continuing on. The wave itself persists, the material within it changes. It is a pattern, not a thing. What keeps the pattern clean, in M51's case, what maintains those grand, sweeping arms, is the gravitational influence of NGC 5195, the companion galaxy. The smaller object sitting at the end of one of M51's arms, connected to it by a bridge of stars and gas, glowing softly in photographs like a jewel hanging from a hook. NGC 5195 is not just decorating the scene, it is actively shaping it. Its gravity, as it passes through and around M51's disk, drives and amplifies the density waves. It compresses gas, triggers bursts of star formation, maintains the coherence of the arms. Without it, M51 might be a more ordinary spiral, less grand, less defined. The collision, and it is a collision, a gravitational interaction that has been ongoing for hundreds of millions of years, is the mechanism of the beauty. NGC 5195 is responsible, in a real and physical sense, for the visual quality that has made M51 famous. Think of it this way. Imagine you are watching a whirlpool in water, a real one, a circular current drawn down a drain or around a submerged obstruction. The shape is there because something is driving it, some force is organizing the water into that spiral. Without the force, you would just have a flat, still surface. The whirlpool in the sky is the same, except that the force is a galaxy, and the organizing is done by gravity across distances measured in thousands of light years, and the timescale is measured in hundreds of millions of years. Models of M51 and NGC 5195 suggest that the companion made a passage through or behind M51's disk a very long time ago, hundreds of millions of years, and that the tidal forces from that encounter stretched and sculpted M51's arms into their current form. The two galaxies are gravitationally entangled now in an ongoing interaction that will continue to unfold over cosmic time. Eventually, not soon, nothing in galactic dynamics is soon, NGC 5195 will be fully incorporated into the larger system. Its stars, its gas, its dark matter halo will be folded into M51's disk. A minor merger in the terminology of galaxy evolution, a quiet act of cannibalism stretched across an almost incomprehensible span of time. The smaller galaxy is being consumed. It is happening slowly, gently, in human terms, inexorably in cosmic terms. What we see in photographs is a snapshot of that process. The companion, still distinct, still separated enough to be counted as a separate object, but gravitationally committed to a future in which it will no longer be separate at all. And here is the connection that ties the whole story together, the thread that runs from the beauty of M51 through the collision with NGC 5195 all the way to the strange and haunting possibility of a planet 28 million light-years away. The gravitational interaction does not only make the spiral arms beautiful, it also makes the galaxy more violent in ways that matter enormously to the question of what kinds of stars exist there and how extreme their deaths can be. When gas is compressed by density waves driven by NGC 5195's gravity, it collapses into new stars. Some of those stars are massive, very massive. Blue supergiants, stars many times heavier than our Sun, burning through their fuel at a ferocious rate. Stars that live briefly and die spectacularly. When a massive star exhausts its nuclear fuel, its core collapses in a fraction of a second, and the outer layers are blasted away in a supernova, one of the most energetic events in the universe. The collapsed core that remains becomes either a neutron star, or, if massive enough, a stellar mass black hole. And what do those neutron stars and black holes do when they find themselves near other stars? They pull material off them. If a neutron star or black hole is in a close orbit with a companion star, a massive donor, perhaps a blue supergiant, which are exactly the kinds of stars that form in enhanced star-forming regions like the arms of M51, The compact object's gravity is strong enough to strip gas from the companion's outer layers. The gas falls inward, accelerated by gravity, heated to extreme temperatures, and emits X-rays. Powerful X-rays. This is the X-ray binary. This is the ultraluminous X-ray source. And the inner region of that accretion zone, the tiny, incredibly hot disk of infalling material around the neutron star, or black hole, is the pinpoint emitter whose size is comparable to a planet. So the chain goes, NGC 5.195's gravity compresses gas in M51's disk. That compressed gas collapses into massive stars. Those massive stars die in supernovae and leave neutron stars and black holes. Those compact remnants, if they're in the right kind of binary system, become ultraluminous X-ray sources. And those ultraluminous X-ray sources, because their emitting regions are so tiny, can be completely eclipsed by a Saturn-sized planet. An eclipse that Chandra can see from 28 million light-years away. The collision is the planet's parent. Not directly, not in a simple cause and effect line, but in the longer, stranger logic of the universe. The gravitational violence that makes the spiral arms beautiful also enriches the galaxy with exactly the kind of extreme dead star systems that make this detection possible. Rosanne DiStefano and her team at the Harvard-Smithsonian Center for Astrophysics found their candidate not in a boring, isolated, quietly rotating galaxy. They found it in a galaxy currently being sculpted by a collision, in an ultraluminous X-ray source that exists because of that collision's downstream effects on star formation and stellar evolution. Beauty is violence. The planet is found in the wreckage. The shadow falls across a dead star's death glow in a galaxy that looks perfect precisely because something is tearing through it. There is something worth sitting with in that. The prettiest thing in the amateur astronomer's sky, the object Messier catalogued as a nuisance in 1773, that Lord Rosse sketched in awe in 1845, that has been on observatory walls for 150 years, turns out, on closer inspection, to be a scene of ongoing chaos made geometrically exquisite by the mathematics of gravity. We look at it and see order, pattern, beauty. The universe is making something extraordinary out of disruption. And somewhere inside that disruption, if Rosanne DiStefano's 2021 paper in Nature Astronomy is right, there is a planet, a Saturn-sized world orbiting at tens of astronomical units from a neutron star or black hole in a binary system that is itself the product of a stellar death that happened because of the same gravitational forces that are shaping those arms. The planet has a year that might last decades. It circles a source of X-ray light so intense that astronomers on Earth, 28 million light-years away, could notice it going dark for 3 hours. We will not be able to confirm this in our lifetimes. That is the haunting part, and it is worth saying again clearly. The team estimated that if the orbital period is what the geometry of the detection suggests, the next transit and the next time the planet would pass in front of that X-ray source from our line of sight would happen in roughly 70 years. That is not a comfortable wait. That is longer than most careers, longer than most human lives measured from the moment of this reading. The confirmation, if it ever comes, will be read by people who are children tonight, or who have not yet been born. The science does not wait to become comfortable. It offers what it has and moves on. And what it has right now is a strong candidate. A dip in the X-ray brightness of an ultraluminous source in M51 that lasted 3 hours, dropped to essentially undetectable levels, recovered symmetrically, and showed no energy-dependent absorption. The achromatic quality, the greyness of the eclipse that argued against a gas cloud and pointed toward a solid body. A single event. One transit in years of archival Chandra data, and the conclusion that if this is what it appears to be, it is the first planet ever identified outside the Milky Way, farther from Earth than any planet ever detected, by a factor of roughly 10,000. That is where it stands, not confirmed, not dismissed, a haunting possibility documented in a peer-reviewed journal, acknowledged by the community as a candidate, and currently waiting for a future that is roughly 70 years away. But here is the part that looks forward, that opens a door instead of closing one. The X-ray transit method, if this candidate holds up even as a candidate, if the technique is real, if the logic is sound, which the team argued carefully that it is, opens a window that did not exist before, not just to M51, to every nearby galaxy with bright X-ray sources, to the Andromeda Galaxy, to the Triangulum Galaxy, to the dozens of galaxies within the local group and beyond. Every ultraluminous X-ray source is, in principle, a potential target. Every compact object binary with a tiny emitting region is a place where a planet's shadow might fall across a beam of X-rays. You would not see the planet, you would not photograph it, you would not measure its atmosphere or its color or its surface temperature, but you would know it was there. You would know a world was passing through that tiny, bright point, darkening it for a few hours, announcing itself by its absence. This is a new kind of planetary science, a kind that is not about our own galaxy at all. Extragalactic planet hunting, the search for worlds in other galaxies, has for most of the history of astronomy been purely theoretical, a category of question you could pose but not answer, because the distances involved made detection of any kind essentially impossible. An ordinary optical transit at 28 million light-years produces a brightness change so small it is billions of times below the threshold of any instrument we have. You would need to resolve individual stars in another galaxy with optical precision, and you cannot, not at that distance, not yet. The stars blur together, the galaxy is a smear of light, not a collection of individual points. But X-ray binaries are different. Their compact object cores are so luminous, so point-like, so geometrically suited to being eclipsed by a planet-sized object that the detection is possible even when the individual stars cannot be resolved. Chandra, launched in 1999, was built to do exactly this kind of work, to resolve X-ray sources in other galaxies, to isolate and monitor individual points of X-ray light inside objects that are, in visible light, just small smudges in the sky. And it turns out that this capability, which was designed for entirely different purposes, the study of X-ray binaries, of stellar populations, of the conditions inside other galaxies, has inadvertently created the conditions for finding planets in those galaxies. It is a reminder of something important about science. You build an instrument for one reason, and it opens a door you did not know was there. The Chandra X-ray Observatory was not built to find extragalactic planets. It was built to see the X-ray universe, the hot and violent and extreme cosmos that is invisible to our eyes and to ordinary telescopes. But in seeing that universe, it made a detection that no optical telescope could have made. The door was there, it just needed the right kind of eye. And that raises a possibility that is worth turning over slowly as you drift towards sleep tonight. If there is one candidate found in one galaxy with one instrument in one archive dataset, what might be waiting in all the rest? M51 is not the only nearby galaxy with ultraluminous X-ray sources. It is not the only place where black holes and neutron stars are pulling gas off their companions and emitting X-rays bright enough to monitor from Earth. There are dozens of galaxies close enough in astronomical terms for Chandra to resolve individual sources, to isolate the light of single compact objects and watch it vary over time. And if even a fraction of those sources are orbited by planets, and there is no particular reason to think M51 is exceptional in this respect, then the universe is full of worlds we cannot see, circling stars we cannot name, in galaxies whose light takes tens of millions of years to reach us. The planets are everywhere. We have always suspected this. The discovery of 5,000 confirmed exoplanets within the Milky Way, every single one of them discovered in the past few decades, with the vast majority within a few thousand light years, has shifted our sense of what is normal. Planets are not rare, they are common. They form around all kinds of stars, in all kinds of systems, in all kinds of galaxies. There is no reason to think that the Milky Way is exceptional, that planets are a local phenomenon, that the universe becomes barren at the edge of our galaxy. The opposite seems far more likely, but demonstrating it, pointing at a specific world in a specific galaxy and saying, this one here has a planet, that is another matter entirely. M51 ULS-1b may or may not be confirmed in 70 years. It may not be a planet at all. Science is honest about this. The team was honest about it. The archiving of a single transit event cannot be called a confirmed detection. The community has been careful with the language, and so should we. But the method is real, the logic is sound, and if this candidate is wrong, the next one found by the same technique might not be. The archive of Chandra data from M51 and other nearby galaxies is enormous, years of observations accumulating in a database that continues to grow. Other researchers are looking. Other transits might surface in M51 or in the 50 or so nearby galaxies that Chandra has imaged with sufficient resolution and cadence to make this kind of search possible. The frontier of planet hunting just moved 28 million light-years outward. That is not a metaphor, that is a number, and it moved there through the Whirlpool. Through the galaxy that Charles Messier catalogued as a smudge in 1773 without any sense of what it was. Through the galaxy that Lord Rosse sketched in 1845 with his enormous metal telescope in County Offaly, capturing the spiral for the first time in human history. Through a galaxy that has been called beautiful for 150 years, whose beauty we are now beginning to understand as a byproduct of an ongoing collision, a gravitational interaction that has been compressing gas and triggering star formation and creating extreme stellar remnants for hundreds of millions of years, through a single ultraluminous X-ray source, a neutron star or black hole devouring a massive companion whose inner accretion zone was briefly, completely, silently darkened for 3 hours by something Saturn-sized passing in front of it. The shadow of a world cast across a dying star's glow in a galaxy being slowly eaten by its neighbor. Wherever you are right now, whatever the hour is in your corner of the night, think about what it means that we could see that. That a team of astronomers sitting with data from a telescope in orbit around the Earth looked at a stream of X-ray photons from 28 million light-years away and noticed a 3-hour absence. Not a faint dimming, not a fractional decrease requiring careful statistical analysis. An absence. Something blocked the light completely and then it was back, and the shape of that interruption told a story about a world. We are very small. Our instruments are, on the scale of the universe, tiny. Our entire planet is a pale dot, to borrow a phrase that has worn its truth into something almost invisible from overuse. And yet we built a telescope sensitive enough to count individual X-ray photons from a galaxy whose light left before our ancestors existed as a species. We built the mathematics to interpret a 3-hour dip in those photons. We had the curiosity to look at archived data from a source that had already been studied for other reasons and ask whether anything interesting had happened there, whether the record of photons told a story nobody had noticed yet. Rosanna Di Stefano and her team asked that question. The data answered it. The answer was maybe, a candidate, a possibility, a shadow at 28 million light-years. There is something humbling about that and something wonderful. The humbling part is obvious. Maybe a 70-year wait, no confirmation in sight. But the wonderful part is this: the universe was there the whole time. The planet, if it is a planet, was orbiting that dead star before humans existed. The X-rays it blocked were traveling toward us for 28 million years before anyone was here to receive them. The spiral of M51 was being shaped by NGC 5195's gravity long before there was anyone on Earth who could look up and find it beautiful. The universe was doing all of this without us, in the dark, in silence as vast as the spaces between galaxies. And then we looked. That is what makes this moment worth lying quietly with. Not just the discovery, but the looking. The fact that a species on a small planet in an unremarkable spiral arm of a medium-sized galaxy built instruments capable of noticing a 3-hour shadow in another galaxy. That we had the patience to archive the observations, the skill to analyze them, the honesty to say candidate rather than confirmed, and the imagination to understand what the candidate would mean if it turned out to be real. The Whirlpool is there right now, even as you are reading this, even as the lamp dims and the quiet settles around you. 28 million light-years away, its arms curling around a bright center, its companion, NGC 5195, hanging at the end of one arm, drawn slowly inward by a gravitational attraction that has been operating since before the first multicellular creatures appeared on Earth. Somewhere inside it, an ultraluminous X-ray source is burning, a neutron star or black hole pulling material off a massive companion in a continuous violent act that emits X-rays in all directions, including the direction of Earth. And somewhere in that system, if the 2021 paper is right, a planet is orbiting, a cold, dark world, perhaps roughly the size of Saturn, following a slow ellipse around a dead star with a year that might last decades. It doesn't know we found it. It doesn't know anything. It is just there, following the mathematics of gravity, as it has been doing perhaps since before our sun ignited, circling a system we will not be able to confirm for 70 years in a galaxy whose light reaches our eyes as a faint smear near the handle of the Big Dipper. But we know about it, or we might, and that is extraordinary. Back at the beginning of this, I asked where you're listening from. I hope you've stayed comfortable, wherever that is. I hope the hour is late enough that this is drifting into the background of your thoughts, becoming part of the soft texture of an evening. You came here with a question. A first planet in another galaxy. How can you even find something that far away? What does a beautiful spiral have to do with any of this? And I hope by now those questions have answers that feel solid enough to carry you toward sleep. The how of it is the X-ray trick. A tiny source, a total eclipse, a signal strong enough to survive 28 million light-years of travel. The what of it is M51 ULS-1b, a candidate Saturn-sized world in an ultraluminous X-ray binary in the Whirlpool galaxy, detected in a 3-hour achromatic dip in Chandra data, published in 2021 in Nature Astronomy by Rosanne Di Stefano and her colleagues at the Harvard-Smithsonian Center for Astrophysics. The why the Whirlpool of it is the collision, NGC 5195, the companion galaxy that has been passing through M51's disk for hundreds of millions of years, sharpening the arms, compressing the gas, triggering the star formation that creates the massive stars that die as supernovae and leave the neutron stars and black holes that become the X-ray binaries that have the pinpoint emitting regions that can be eclipsed by a planet. The beautiful and the violent are the same thing. The perfect spiral is a slow catastrophe. And in the middle of the catastrophe, if we are very lucky and the geometry of one particular orbit aligns with ours, a world casts a shadow we can see. If any of this pleased you or calmed you or gave you something soft and strange to think about as you close your eyes, A like and subscribe helps this sleepy little channel keep going. Small creators like me rely on your support, and it really does make a difference. And leave a comment if you like. Tell me where you're listening from tonight and what time it is in your corner of the world. I read them, and I find it a quietly moving thing to imagine all the different places where these words arrive. Close the books, dim the lamp. Class is over, sleepy scholar.